Good morning. Okay, let's continue. And this is probably the last lecture with meaningful content. As a matter of fact, you can relax. What's going to be covered today is not going to be covered in the exam. Okay? Yeah. So, first of all, just a picture here. We've been, I think you have heard or have been using lots of big names, particularly those French names. For example, Laplace and Lagrange. Okay. And this is actually the Eiffel Tower. Basically, if you look around there, I've never been there. All these famous French mathematicians, scientists' names. So those are So those names you're probably going to see, in several other courses. They just have so many contributions. Yeah, I believe the Euler's name should be there somewhere there too. Okay. Yeah. Okay. So just a quick review as what we have learned in the last lecture as to a Fourier series. Okay. So Fourier series is gonna. So what's covered last lecture is part of the exam. Okay. Yeah. Today's one's not gonna be the exam one. In the last lecture, we learned for a periodic function or signal. Okay. Suppose it has a period, okay, of t naught. Okay. Then we can decompose or we can express, okay, this periodic function, this signal, okay, with a sum of sines and cosines. All right. So that's what we did. This is basically called Fourier series for periodic function or periodic signal. All right. And of course, you have the formula for an and the bn. Okay, so I'm not going to write anymore. Okay, so now the next one here is let's write this formula just slightly here differently. Okay, we're going to write it using this complex exponential function, right? Yeah. So which is basically what I call complex form of a Fourier series. Complex form. Okay, so before we write the complex form, just a quick review as to the Euler's formula. So Euler's formula is what we learned when we learned complex number, and that formula basically saying Ej, okay, theta equal to cosine theta plus j sine theta. Okay. So now what I'm going to do is let me change the theta to t. So Ejt equal to cosine t plus j sine t. And then E negative jt, okay, E negative, that would be basically cosine negative t plus j sine negative t, right? And cosine is even, so this is just cosine t. Sine t is odd, so that's negative sine t, okay? Yeah. And then, okay, when you add these two together, and when you add these together divided by 2, so you will get basically cosine t equal to ejt plus e negative jt over 2. Okay. Similarly, sine t, okay, can also be expressed using this exponential ones here. So that'll be ejt minus e negative jt over 2j. Okay. Does that ring a bell? Yeah. Yeah. Very easy to verify. Just this minus that, you divided by 2. This minus that, cosine cancel, right? And sine minus negative is 2 negative sine, 2 sine t, and multiply by j. So divided by 2j, you get sine t. Okay? Yeah. Okay. So now what I guess what I'm trying to do is, here is cosine n omega naught t. Here is the sine n omega naught t. So I'm gonna basically try and replace this cosine and sine here with this formula here. All right? Yeah. So as a matter of fact, one of the things I think sometimes the question asked is, when you learn complex number, a lot of time people ask is, if the real world is all about the real, there's no complex number, and complex number imaginary, then why would you learn complex number? See, this is one of the reasons here. See, this ejt or something like this, or ej omega t like the other one there, they don't exist, but they are, if you look at this expression here, they are basically some kind of a fundamental things or fundamental component for this cosine t, sine t here, right? So a linear combination, this expression is a linear combination, right? It's a linear combination what? It's a linear combination of ejt, e negative jt. This one here is a linear combination, and it's just 2j at here, right? And that'll give you cosine t, sine t. Basically, the underlying the concept is the real things, which is basically what you see. Actually, on behind of that, it consists of some of these fundamental things like this, right? So, which is of course you don't see that, right? Yeah. So that's kind of the reason. Many times the mathematics sometimes it looks not so very useful in real life, but really they are hiding behind contributing to those useful ones there, right? Yeah. And the other thing is, if you remember, why would you like to deal with this instead of just dealing with cosine sine? Is because if I ask you to multiply or add or divide two sine or cosine things, right? It's trigonometry. It's not easy to calculate. However, if you convert things into these exponential things here, the addition, the subtraction will be much easier to do it. Okay, so in other words, my cosine n omega naught t, compared to this one here, that'll be e j n omega naught t plus e negative j n omega naught t over 2, right? Okay, that's this same formula, basically just plugging n omega naught t here. Okay, so then I'm gonna rewrite my f of t. So rewrite my f of t in terms of this new formula. Okay, so an, still the an. Okay, so then we're going to replace the cosine n omega naught t, okay, with this Euler's. Okay, so this is an cosine n omega naught t, and you have the other portion which is a bn sine n omega naught t. So sine n omega naught t. So looking at it here, it's gonna be e j n omega naught t minus e negative j n omega naught t divided by 2j. Right? Okay, so now I have this exponential, complex exponential showing up, okay, in the Fourier series expansion. Yeah. So this is not clean enough yet. Let's clean it up. Okay, let's clean it up a little bit. Okay. So you have a lot of e to the power of j n omega naught t, and there's another one e to the power of negative j in omega naught t. So we're going to group the similar terms for this one and group the similar term for this one here. Okay. And if I do that, I'm going to end up with, okay, this is an minus jbn over 2 ejn omega naught t. Okay. So basically, before I do this step here, what I did is this is a 1 over 2j at here, right? There's 1 over 2j. So you can basically 1 over 2j equal to what? Equal to negative j over 2. Okay. So then you can do this simplification, okay? Yeah. So then this is basically an plus jbn over 2. Okay. And e negative n negative j omega naught here. All right. There we go. So that's a new look for this Fourier series. Okay. Yeah. We're not quite finished yet. Yeah, it's almost there. Any questions? All good? Yeah. Okay. So now let's define ourselves. Okay. Define ourselves a new things here to simplify this expression here. So basically, you see. This quantity here, there's a positive. This is n omega naught t. So the n goes from 1 to infinite, and basically this guy goes from 1 to infinite here, right? And this one here, this is a negative n omega naught t. So when n goes from 1 to infinite, and this quantity goes from what? From negative 1 to negative infinite, right? Yeah. So the next step is what we're trying to do is we're going to try to simplify the writing here. Basically, we're going to let Cn equal to this quantity. Okay, for this quantity here. So as if we have a coefficient set here. Okay, then as n goes to 1 infinite, okay, your coefficient varies with respect to the n value from 1 to infinite. Okay, for this particular term in here, right? And the second one here, as we see that as n goes from 1 infinite, this one here goes from negative 1 to negative infinite. So for this quantity here, so we define it as c negative n. Okay, we define it as a coefficient of c negative n here. Okay, so basically, as n goes from 1 infinite, this term is like going from negative 1 to varies according to negative 1 to negative infinite. Okay? Yeah. Then altogether, right? So this from here to here becomes a naught, okay, plus, okay, n equal to 1 here, cn ejn omega naught t plus c negative n e negative j and omega naught t. Okay. Yeah, so that looks much better. Okay. And better yet, we can simplify it one more step. Okay. So one more step here. So one more step basically, just look at the way it varies. So the first one changes from 1 to infinite. Second one changed from negative 1 to negative infinite. So altogether, okay, you can write everything altogether as this. Instead of this n goes from, okay, instead of this, actually you don't need this one anymore. Instead of so basically what happens is, instead of n starting from 1, you can let n go from negative infinite to positive infinite. And altogether, Cn at here, like this. Okay? So let's see if that makes sense or not, right? Yeah. First of all, let's look at this the particular case. When n equal to 0, So I got C naught, which should be the value of A naught at here, right? Should be a value of A naught. When n is positive 1 to infinite, this guy is a Cn. Basically, when n is 2, you got C2. That's basically that term over there, right? When n is negative, let's see, what do we have? C, instead of n at here, C becomes C negative 2 here. So this is basically that term over there, all right? So you see, this thing here basically represents that long expression over there, okay? Yeah. Now, what we just derived here, okay, what we just derived this guy here, this is basically f of t here, okay? F of t equal to this. So f of t equal to this, that's the so-called complex form of the Fourier series, okay? The complex form Fourier series, right? Yeah. So the same question should be asked is, why do you use a complex form, right? Yeah, why not just stick with this one here? Same idea, same explanation. You look at this one here. This is all involving sine and cosine trigonometries here, okay? And this one here, you don't see the sine and cosine. There's only exponential, complex exponential here. So in terms of the calculation, analysis, okay, system analysis, and this term here turns out to be much simpler to deal with or to handle than the typical trigonometries, you know, sines and cosines, right? Yeah. So this is why there's an advantage here to write it into this complex, okay, form of Fourier series, okay? Yeah. But you should understand is they all represent the same thing, all right? Yeah. So okay, we know the Cn now. We know the C naught. The question is, what will be the Cn here, right? What will be the Cn? What will be the coefficients for the Cn here? There are different ways of deriving the Cn at here. Okay, one way of deriving the Cn is, where's the Cn from? Cn is from this guy here, right? It's from here. And where's the An? Where's Bn? We derived the A and Bn from previous lecture. So if you remember, basically An, okay, equal to 2 over t, okay, 0 to t naught, okay, the t naught is a period, f of t cosine n omega naught t dt, and bn is 2 over t naught, 0 to t naught, f of t sine n omega naught t. So what you do is basically you can just substitute, okay, this a and bn, okay, into this formula for the Cn, okay, and then you will be able to get an expression for the Cn at here. Okay, so that's one way of doing it. The other way of doing it is here's an expression here, right? This expression. Then what you do is you multiply each side. Okay, multiply each side by e to the power negative j n omega naught t. Okay, and then you integrate over one period. Okay, and you'll get it. But let me write down this first thing first, okay? So if you sub this one into it, okay, I'll skip some details here. You can look at my lecture notes as to how in the middle of the steps here. So you'll get Cn equal to 1 over t naught, 0 to t naught, f of t, e negative j, negative j n omega naught t dt. Okay, yeah. So that's the Cn at here. Okay. Okay. Now the other way, as I said, the other way of doing it is you multiply each side. You do it, right? So the actually, if you remember in the previous lecture, what we mentioned is, when we have a set of cosine x, cosine t, sine t, cosine mt, sine mt. Remember what we call this set here? This set is called, they are orthogonal, right? Integral of a pair, any pair of these two over one period, they're orthogonal. As a matter of fact, okay, this e negative j n omega naught t, or e positive j n omega naught t, and you give n certain values here. these pairs are also orthogonal. Okay, also orthogonal. Yeah. So they retain the same kind of properties, right? Okay. Okay. So that's basically Cn and here. Okay. And if you know the property, if you remember the other way of writing this one here, or you see it in Tom's textbook, instead of 0 to T naught, it can also be written as negative T naught to over 2 or to positive T naught over 2. All right? Yeah, it's the same thing. So what's important next is, okay, now we have this exponential, complex exponential form, and we have the Cn expression, right? Often in time, what you really need is, okay, so what does this Cn represent? You know, what information can we extract out of here? So Cn is the coefficient, okay, for each one of the term in here. Just like An, Bn is a coefficient for associated cosine n omega naught, sine n omega naught, right? So then basically what happens here is n omega naught, you plug in the n value, there's a frequency here, right? You plug a different n value, multiply that with omega naught, you get a different frequency. At that frequency, there's associated coefficient Cn. So what you can do is you can think of a Cn here. We can think the Cn, okay, as a function of n omega naught, right? As function n omega naught. So you know, you put in different n value, you get frequency, and then you have a certain Cn. So technically speaking, I can plot Cn versus the n omega naught, right? So we can plot Cn, right, versus n omega naught. Okay, yeah. Now, however, okay, things are not that always so neat. Basically, the Cn, if you look at the expression, the Cn here, okay, the results of the Cn often in time is also a complex number. Okay, so Cn, okay, in general, okay, is complex number. Okay, in general. Okay, but for certain signals, it turned out that the Cn is not a complex; it's just basically a real. Okay, so if a Cn is a complex number, then you won't be able just to plot a complex number versus a frequency. So the way that we depict or describing a complex number is what? So when you have a complex number, so how do we describe a complex number? We often in time describe complex number as its magnitude and the angle, right? The angle associated with the complex number. Okay? So instead of plotting directly the Cn versus the frequency, n omega naught, you can plot the absolute value, or the so-called the magnitude, okay, versus the frequency, and also this phase versus the frequency. Okay, so that's how you can depict this Cn here. Better yet, okay, there's a couple of things here. Right? If f of t is real, okay, if f of t is a real function, so in other words, f of t could be not a real function, could be a complex function, right? But if f of t is a real function, then if I go back over here, okay, the a and bn will be real values, and this Cn basically is complex, right? And what's C negative n? So C negative n is this guy here, right? So if you compare this Cn with C negative n here, what do you call them? Conjugate, right? They're conjugate. So this Cn, basically, the conjugate of Cn equal to this C negative n. Okay, they're conjugate. If they're conjugate, okay, if they're conjugate, then that means the magnitude of this, so the magnitude of Cn will be the same as the magnitude of the C negative n. Okay, if they're conjugate. And if they're conjugate, the angle, basically the phi angle here. So maybe I'll write it as this way here. So this is the phi angle is basically the angle representing the Cn. If they're conjugate, this angle for the Cn is equal to the negative c negative n. Right? Let's think about the complex plane. So here is a complex number a plus jb. Where is the conjugate? It's here. Right? And what's the theta here? That's the theta here. And what's this guy here? Negative theta. Right? Okay? Yeah. So that's basically the kind of idea here. Now, because I know what my Cn is, if I know what's my Cn, Cn is an minus jbn over 2, right? So then, what would be the magnitude for this guy? Basically, magnitude Cn is the magnitude of this one. And magnitude Cn of that one, that equal to what? 1/2 root an squared plus bn squared. So that's a connection there, right? That's a connection. Okay. Yeah. Yeah. Okay. So now let's take a look at one example here. Okay. Yeah. So let's say, suppose I have a periodic function. Okay. So here's how the periodic function changes. This is 2, negative 2, and this is 1, okay, and this is 8 at here. All right. So basically, the function has a period of 8, right? Has a period of 8. And this is kind of a so-called gated function here. Okay, if you just look at this one here as a gate, right? Yeah. Then now let's try to get the Fourier series, okay, for this one. So you can use the formula from previous lecture to derive, but we're going to derive the complex form for this Fourier series, right? Yeah. So first of all, okay, basically we need to derive the Cn. And in particular, we need to know the C naught, right? The C naught. Okay. So let's derive this C here, because I will try it C naught first. Okay. So according to the formula, okay, Cn, where's the formula? So the formula is this one here. Okay. Formula is this. So if I try to derive C naught, I'm going to replace the n with 0. Okay. So let's replace that with 0. So 1 over t. Okay, so in this case here, your original formula is 0 to t naught. But as I said, you can also do is negative t naught over 2 to t naught over 2 here, right? So in this particular case, we'll do that. So negative 8, okay, to positive 8, and f of t, okay. Hang on a second. No, negative half, negative 4, right? And then negative t over 2. Okay, half. Yeah. So f of t e negative g0 omega naught t dt. Okay, so t is 8, so this is negative 4 to 4. And f of t and dt, because this is 1 here. And you don't need to integrate from negative 4. This is 8, this is probably 4 here. So you don't need to integrate from negative 4 to 4, just have to integrate from negative 2 to 2, right? Yeah, so this is basically 1 over 8, negative 2 to 2. And between negative 2 to 2, the value of f of t is 1. So just replace the f of t as 1 here. Then overall, this is what? 2 minus negative 2 is 4. 4 over 8 is 1/2, right? It's 1/2. Okay, yeah. So that's C naught. Okay. So now let's take a look at the Cn here. So Cn is 1 over t, negative t over 2, t over 2. Okay, f of t. Use the general. Okay. Use the general one now. Okay. Yeah. And omega naught. Remember, omega naught is basically 2 pi over t. In this case, it's 2 pi over 8. Okay. Yeah. Or it's pi over 4. Okay. Pi over 4. Okay. Okay, so similarly for this integral, this is 1 over 8, negative 4 to 4. However, you don't need to integrate a 4 to 4, you just have to integrate from negative 2 to 2, right? And between negative 2 is 1, so this is negative j, and you can replace the omega naught with pi over 4 at here, and t and dt. So that's a very simple integral, basically involving an exponential term here. So you treat this j and pi over 4 as a constant, right? As a constant. So the results of the integral is fairly straightforward. So you're going to end up with this guy here, okay? So I'll give you the results here, which is sine, okay, pi over 2n over n pi. Okay, so we're going to have this guy here. Okay, so you look at this Cn at here. For this particular case, this is not a complex number, right? This is a real number. There's no j involved here. Okay, yeah. So you plug in an n value into it from negative infinite to positive infinite, and you at every value n you'll get a real number. So if you plug in a negative n, you probably get a negative value. But if you plug in, it's basically the Cn changes here, right? So what we really need is we want to plot this. We want to plot this Cn, okay, absolute value Cn, right, versus n omega naught here. Okay. Or n omega naught in this case is n pi over 4. Right. We also want to plot this value of Cn, okay, versus n omega naught here. Okay, versus this. Right. So if I before we do the plotting here, let's do a little observation in here, okay? Yeah. So let's see if I plug in an n value into here, and yeah, I don't have a specific numbers here, but let's see if I plug an n equal to, let's see, this is 0, 1, 2, 3. Yeah, if I plug in n equal to 3 into it, okay? So can you calculate what's the Cn value? So if I plug in Cn into 3 here, what do we get? This is 3 pi over 2. Negative 1 over how much? 3 pi, right? Yeah. That's right. So for this one here, what's the magnitude? The magnitude will be 1 over 3 pi. And what will be the angle then? Right? Remember, you have to find the angle from the complex plane. Okay, so this is a complex plane, real axis, imaginary axis. Where would that negative 1 over 3 pi located? Where would that be located? On the real axis. Exactly. Real axis, but it's on the negative side here, right? So maybe it's here. Okay, if it's here, what would be the angle for that? Pi. Right? It's pi. So basically now you can imagine now, right? You can imagine. So the value will be oscillating between a positive and negative value. So for positive value, the angle will be how much? 0. For negative value, it will be pi, right? However, okay. However, there's one little thing here is if I plug, okay, if I plug n equal to negative 3, okay, if I put n equal to negative 3 into it, so the C negative 3, what will be the C negative 3? So C negative 3 at the bottom is negative 3 pi. And sine negative 3 pi over 2. What's the sine 3 pi over 2? Sine negative, this guy actually is a positive value, right? So it's still 1 over this. That make sense? Yeah. So if you look at this guy here, this is also a negative number, right? This is also a negative number. So if this is a negative number, then technically speaking, the angle for this one here, I can also call it pi here, right? Also call it pi. However, one of the things I mentioned at here is when you have a real here, what's the angle relationship between the C and the C negative n is what? There is a negative difference. So essentially, for this one here, you would use a negative pi at here. Does that make sense? Actually, yeah, you can go from here to here, right? Negative pi. Okay? Yeah. So that's basically the way you draw it. Okay? But the magnitude is still the same as that one, magnitude. Okay? So overall, you can, if you plot them out, okay? I don't have this one here, but in my yeah, this lecture I just finished last night. So you will end up with a drawing of this Cn with n omega naught. Then you will end up with something like this. At omega at n equal to 0, the value is at omega is 0. The value is 1/2, right? It's 1/2. So this is 1/2 here. And then if you keep going as you're increasing n value here, so at the next omega naught, which is pi over 4, which is this, and then the next one is 0, and the next one at n equal to 3, it's somewhere here. This is n equal to 3, so that's 3 pi over 4, and this value is what we just find, 1 over 3 pi, Now, because the absolute value of Cn equal to absolute of C negative n, so it's actually symmetric. It's actually symmetric. For this plot of Cn. And the phase angle, you can also do the plotting here. But the phase angle is not symmetric. The phase angle is odd, basically. Yeah. So the phase angle, it's all 0, 0, 0, and up to here, there's a value here, pi. So that's the phi value. And the next is also pi here, and on the other side, it's the other way. It's the other way. So anyway, look at the lecture notes just regarding, but that's basically how you make the drawing here. Make the drawing. So what happens is when you look at this plot here, you will have a pretty good idea as how much of this contribution at each one of the frequency at here, right? Yeah. And basically the base one here, 1/2, has the most magnitude. Right? Okay, so that's basically a complex form of Fourier transform, right? Fourier transform. I think I'm running out a little bit of time here. But I really wanted to cover this Fourier transform because the reason is those people who go into civil and maybe mechanical, you're not going to have any chance of learning Fourier transform anymore, right? So that's kind of or maybe you don't. So let's start it, and we got time for next lecture. Yeah, as a matter of fact, I also have one more big topic I couldn't cover anymore, which is the systems of linear equations. So we're dealing with differential equations 1, right? Yeah. In certain situation, when you have multiple degree freedom, you will have you will basically have a set of linear differential equations. The question is, how do we solve that? So Fourier transform, first of all, where does Fourier transform from? Fourier transform basically comes from the idea is how do we deal with aperiodic function, right? So if I have an aperiodic function or signal, so let's say this is f of t here, So this is f of t, is aperiodic, basically it doesn't repeat itself, it's just there. And so the only question is, okay, how can we analyze this kind of function? For periodic function, you use a Fourier series, and you can find, oh look, I got this linear combination of sine and cosine with the multiples of the fundamental frequency omega naught, right? Yeah. And for aperiodic function or signal, you actually have a similar things. You know, it must contain some kind of frequencies in it, right? So the only question is, how do we analyze that? So what we do is we do this, okay? We construct ourselves. Okay, we construct a ft naught. We construct a periodic function based on this guy. So this is what happens here. This is what f of t here, and the f of t naught. Okay, you construct f of t naught like this. Okay, this is f of t, right? Then repeat this f of t at every period. Okay, at every period of t naught. Okay, so basically construct a periodic function based on this aperiodic signal. Now, when you construct this one, but one thing you got to be careful is you don't want to, you choose the t naught carefully such that these two adjacent curve or wave, they don't cover each other, right? Yeah. So once we have this now, then the next thing is, okay, okay, what's the Fourier series expansion for f of t naught? So that's okay, right? That's okay. Yeah. So we can derive the Fourier series. So Fourier series for f of t naught t, it's available, right? Because it's a periodic function. And then, okay, so we're going to skip the details for now. And then what happens is, if I let t naught go to infinite, okay, if I let t naught go to infinite, then this f of t naught t will become which one? F of t, right? Yeah, f of t. That makes sense, right? Why not? See, let t naught go to infinite. Basically, this guy here will keep going to the right. So when t is infinite, you can't see that anymore. All you see is this one, right? All you see is going to be this one. Okay. So that's the relationship here between this f of t and the periodic function constructed using f of t here. So the whole idea basically is you construct your Fourier series for this f of t naught, and then we're going to do some manipulation using this limiting process. Okay, and we'll be able to get ourselves a Fourier transform, which is this guy here. Okay. As a matter of fact, that's not quite right. No. No. Yeah, if I do, I wouldn't do this way. Yeah. So, but anyway, so we're going to spend maybe 10 or 15 minutes next lecture to cover this Fourier transform, right? Yeah. And then we'll do a quick review on the whole lecture. Okay. So for those people who's not registering 248, next Monday from 9 o'clock to 12, yeah, and we're going to have a exam jam kind of a session, okay?
Where will the exam jam be?
Oh, right. It's in this classroom. Yeah, I'll send an email to you guys later.